We go into pipeline processor. Let's understand the basic concept of pipeline, right? So let's say, and this is relative to car manufacturing. So what happens is, in let's say, in the creating a car, there are three parts to be done, right? So you build the chassis, and then you build the engine, and then you paint the car, and you're done. Okay, so your car is ready. So you'll first make one car, and then after that you'll do it for second car. You'll build the chassis, you'll build the engine, you'll build the paint. Okay, so let's say one person knows how to do chassis best, one person knows how to do engine best, and another person knows how to do paint best. Okay, now what do you see happening, right? So when this person's job is done, he's still waiting from here to here. He's free, right? As in, he can still do more work, because when engine person is working on the engine, when paint person is working on the paint, that person is free. Okay, so rather than waiting this whole time, as soon as chassis work is done, he can start doing chassis work for the car B. And this is what is known as pipelining, as in, when a certain part of here, when the person is free, he can start working on the next thing. From a processor point of view, you can think of, okay, let's say my memory is free. Can I do some more? Can I read some more data into the memory? My register file is not doing anything, or my ALU is not doing anything. Can I do some more operation on ALU while other parts of the processor are still doing other operation? And that's the basic idea of pipeline. So basically, this chassis person is done now. So for second car, he can start. While for the first car, basically engine work is going on. When this engine work is done, you can start on the second engine work. So basically, you almost can get three times the work done if there are three parts to your car building. It will not exactly be three. We'll talk about the reasons for a processor. But basically, in the same amount of time, you can get almost the three times of the work done if you pipeline it. So taking from here, can we apply the same idea to a processor? And that's what the concept of pipelining is. So basically, what we'll do is, we'll design a pipeline processor by subdividing. So we'll use a single cycle processor, and we'll subdivide into 5 pipeline stages, and approximately 5 instructions then can execute simultaneously, similar to like three people, 3 times the work being done in a car assembly. Similar to that, we'll try to break it down into a single cycle processor into 5 pipeline stages, so that 5 instruction can execute in parallel. Now each stage only has 1/5 of the entire logic, so maybe clock can also run 5 times faster, and latency of instruction is changed, but you will be able to get throughput which is five times faster. So let's see how we can do that. Pipeline may introduce some overhead. This may be extra logic which may be there, or there is another kind of hazard which can be there, which we'll talk about. But in general, we'll be able to improve our throughput if we kind of design a pipeline processor. So let's see how that can be done. Okay. So again, similar to when we were talking about multi-cycle instructions, let's see what are the slowest part of the processor, right? Reading and writing into the memory is the slowest part. ALU also typically is the slowest part, which is the biggest delay. So we'll choose our pipeline stages so that each of these stage will involve only one of those slow steps. Okay. So specifically, as in, if you remember, as in those typically 5 stages are known as fetch, decode, execute, memory, and write back. And these are, if you remember, these are similar to what we had done in multi-cycle stage as well. So you will fetch, decode, execute, memory, read from memory, that means, and write back. These are similar to five stages that we did for load word in the multi-cycle processor. In the fetch stage, the processor read instructions from the instruction memory. Then in the decode stage, processor will read the operands from the register file and decode the instruction to produce control signals. In the execute stage, processor will do the ALU operation, and in the memory stage, processor read or write the data to the memory if applicable, and finally in the write back stage, processor will write the result to the register file if applicable. Okay. So let's see what are the various stages of our pipeline processor. In the single cycle processor, first instruction is read from the memory at time equal to 0. Okay, so first is basically instruction is fetched, then basically decoding happens, then ALU executes the necessary computation, then memory is read or write depending upon the instruction type, and then if required, required register file is written out, and then the next instruction starts, right? So compare this to the analogy of car assembly which we are talking about, right? So these are all the steps which are done, and then the next instruction starts, and then you continue along these steps. What we are trying to do is, can similar to our car assembly, which things were happening sequentially, can we parallelize it? Okay, can we put this in parallel? So what we are going to do in is basically we're going to read the fetch instruction while decode is going on. We will also fetch the second instruction while now execution is going on. Can we decode next instruction and in parallel also fetch the third instruction, and so on, because there are 5 paths in parallel. And as in our car assembly, that allowed us to have 3 times the work done or 3 times the throughput. Will this allow us to have 5 times the work done and make our performance 5 times faster? Okay, so in this pipeline processor, we basically improve the throughput. Each pipeline will basically start here. Okay, so we'll have first fetch instruction, then in second fetch instruction will start here while the decoding is going on for the first instruction. So we should be able to improve our basically throughput by a lot of time, around approximately 5 times, but it's not exactly 5, and we'll understand the reason why it's not exactly 5, but we should at least be able to, it will still be maybe at least double 3 times what that it will be, that we'll understand, but should be able to improve our throughput or performance. Okay, one thing to keep in mind. Okay, so this is one of the important aspects, right? We are thinking we'll be able to do that, but a central challenge in these pipeline system is hazards. Okay, there are some hazards which can happen. These hazards occur when one instruction's result is needed by a subsequent instruction which has not been completed. For example, let's say we have this load word instruction which will load into S2 some data, and then let's say right now this is add S3 and S9, add S9 and S10 to make S3, but rather than let's say S10, it was S2. Okay, what is the problem here? Okay, so basically you are loading this register S2 from the memory and then feeding into the register file. So first instruction will perform like this. Okay, you will have instruction fetch, this will be added, it will be read from the data memory, and here S2 will become available. Okay, but S2 becomes available only here at this point of time, right? But in the second instruction, if you have to do S3 equal to S9 plus S2, you'll fetch the instruction, and here rather than S9 you have to do S2 plus S10, but it's not available because it has not been fetched from the memory yet. So because of this, since it's not available here, this pipelining will cause a problem. In our normal processor, Since the second instruction would have started here, it would have been available. But now since we are pipelining, this S2 is not yet available, and this will cause a problem. So this is a hazard. Basically, you're trying to kind of read, basically you're trying to have next instruction needs the result of the previous instruction, but it's not ready because you are pipelining it, and that creates a hazard. So pipelines will have these hazards. Of course, you will have to kind of make sure these hazards don't occur, and then we'll see how do you do that. Okay. So for a pipeline, we'll talk about how to solve that, right? So now coming back to our pipeline data path, right? So pipeline data path is formed by chopping single cycle data path into 5 stages. So this was our single cycle data path, and we then now have chopped it and created basically first fetch, added a register here to store these values, then decode, added a register to store these values, execute, where the execution or adding or whatever operation you're doing is done, then memory, accessing the memory, then write back. Okay, so we have broken our single cycle into 5 stages so that we can do it in parallel and also improve the clock frequency. Now paths are shorter than a bigger critical path. So we have kind of fetch, decode, execute, memory, and then write back. One thing, so this can work. The only thing is we have to take care of the hazards. So how do we take care of the hazards? We'll go in little bit detail as we go along. Okay. So we have kind of created is basically these stages. Now our instruction, like for example, load word instruction is peculiar because that is what is causing the hazard, right? What is happening here in the load word instruction is that we decode here that we have to do a load word operation, but results get written back into the register file only here. So basically there is this cycle difference. You're decoding here, so, and if you start next execution here, it will not be available because register is written back after the write back stage. So that is kind of peculiar to this, and this feedback leads to pipeline hazard as we saw earlier. Okay, so one other change we are also doing is the register file which is here, we are writing on the falling edge of the clock so that it can write a result in the first half of a cycle and read that result in the second half of a cycle for subsequent insertion. So basically register file, we have made one other change. It's working on the falling edge of the clock. So one addition thing is basically we have to store all the control signals in the pipeline. All the signals associated with a particular instruction we have to store in a big register file, and this is in the add-on because of this area will increase, but for the right reasons, that your throughput will be better. Okay, so in addition to that, control for the pipelines are same as single cycle processor. Nothing you have to change here. The only thing is you have to add pipeline also into the control so that as it moves through, you save those signals for the next. So basically for each of the control signals, the logic is the same, just that you have to add pipeline registers for each of these pipeline through which you are going through, because this otherwise these signals will be overwritten. When next instruction is fetched, these signals will be overwritten. So for this, you can't use the same signals. You have to first register it and then use it so that the previous value is there for the next stage of the previous instruction which is going on. For example, let's say this is fetch. What were our cycles, right? Fetch, decode, execute. Okay. Now let's say second instruction is in first instruction is in execution. So first instruction is in execution and second instruction is in decode. So since it's decode, these values are updated. But for execute, you want the control signals value to be as per its own instruction. So if you pipeline those also, that is good enough for basically having the pipeline control. So both the data path and the control path both have to be pipelined, and by adding these registers which we are talking about. Okay. Now let's go into more detail about this hazard, right? So in a pipeline system, as we are understanding, multiple instructions are handled concurrently. At the same time, you are handling multiple instruction. Now, when one instruction is dependent on the result of another instruction, which has not yet completed, a hazard will occur. So when one instruction is depending upon the result of another instruction, since instructions are running in parallel, if one previous instruction on which this result is dependent that has not completed, the hazard will occur. For example, a register file is written during the first half of the cycle and read, right? So basically, but there are some things which can be done without introducing a hazard. So let's understand that, right? When the hazard will happen. So hazard occurs when one instruction writes a register and subsequent immediately next instruction reads that register. We're talking about load word instruction that can cause hazard because the register has not been written there. In addition to that, this, for example, you are doing add. Now what is happening here is add S8 is equal to S4 plus S5. So next instruction then S2 is equal to S8 plus S3. So immediate next instruction needs this S8. And when is S8 written? So let's see, first instruction does, it fetches, then S4 plus S5, ALU operation happens, and then S8 is written into the register file. So basically S8 is available here. This cycle it is available. But when is the next instruction try in terms of timeline trying to access that data? It is trying to access this data here, which is 2 cycles before, and of course it's not available. So that is when the hazard occur. This kind of hazard where basically one instruction writes a register and subsequent uh, instructions try to read it when it's not ready is known as read after write hazard. So if you're trying to read something which has not been written yet, so it's a read, first you write it, which has not been written yet, read after write hazard. And of course, if you don't do special treatment of this, figure out a way to solve this, you will compute a wrong result because it will access S8 register from where the previous value is there, new value has not been written and will lead to an hazard. So what special treatment can be done for this? So a simplistic solution would be, which is a software solution, is to not do anything. Okay, when you know, okay, I'm reading this, don't wait for 2 cycles. Okay, don't do anything here, don't do anything here, and then fetch the next instruction. Okay, so you kind of add 2 no ops here and then fetch the next instruction. What will happen because of that? Now S8 is ready. Now S8 is ready, so I'm able to read it. So it's kind of one simple software solution will be to add 2 no ops, and then you can do it. But the problem with that is, of course, it degrades the performance, right? Your whole purpose was to improve the throughput, but it won't increase because of this. So that's one of the problem with this. Second is a software has to kind of worry about how, if such a C code is written, software becomes complicated. Software has to kind of understand, okay, when the no op has to be done and write assembly code like that. So it becomes a difficult software. Compiler becomes complicated to kind of do this. So one of the simple ways, doing a no op, but typically this is not done. This is not one of the recommended solution. Okay. So there are other ways of doing that. Let's understand those. Okay. So sum from the add instruction from the ALU is compute where, so it's written in the register file here, but it's actually computed here. Okay. So already it's computed, just that it takes one more cycle before it's written out in the register file. Okay. And where do we need it? We actually need it here itself, right? So for the second instruction, this is already computed here and we need it here. So rather than waiting for it to be written into register files, if somehow we can just pass it directly along here, okay, in the same cycle, it assuming that it will be written to the register file, while in parallel we can just pass it to the next instruction, maybe we can avoid the hazard, right? So basically, that is one of the way, and we'll understand this is known as forwarding. So we should be able to forward the result from one instruction to the next to resolve at least this particular hazard, read after write. If we can just pass on directly, if we see, right, it is already calculated here, and it is needed in the same cycle for the next instruction. So we should be able to forward somehow if we modify the hardware, and we can avoid this hazard, read after write hazard. Okay. So in principle, since this addition is S8 is available here, and this for the next instruction it's needed here, if you can just forward it here, we should be able to avoid our hazard. So in principle, we should be able to forward the results from one instruction to the next to resolve read after write hazard, and we don't have to wait for it to appear in the register file and then read it. Okay. So this way is basically, in principle, if you think in abstract, we kind of should be able to solve it if somehow we can forward the result. Okay. So